vector multiplication, you see Cy. Again here computational complexity is O into the power 2, and also this has a great applications. But we can minimize the computational complexity of this algorithm using the FFT, fast Fourier transform. This algorithm, the matrix vector products can be written as a cyclic convolution of the coefficients of Y and the elements or entities in the circular matrix C. And using the 3 FFTs, 1 IFT and the 2 FFT, this computation can be done in the n log n computational complexity. And the Toeplitz matrices, this is also you see same as circular matrix, but the difference is the first row and first column contains a different elements. And again, the Toeplitz matrix vector multiplication. In this also computational complexity, that is a polynomial computational complexity, O n to the power 2. And again, we can use the concept of circular matrix vector multiplication to compute the Toeplitz matrix vector multiplications. Here, we augment the Toeplitz matrix into the circular matrix of size 2n, order 2n. And you can see here C is a T, S, T, and S is defined. T is the Toeplitz matrix of order n. And capital Y is a block matrix containing all the elements in Y bar, Y and n zeros. You can see C capital Y vector matrix vector product is equal to Ty and Sy. The Ty is the one we need. Again, we have proved this can be performed in n log n computational complexity. First polynomial multiplications, short refers as FEM. Again, the product of P and Q, that is a PQ. The coefficients of product of PQ, that is RS, is a cyclic convolution of the coefficients of P and coefficient of Q. Again, this can be performed, or this can be calculated using the FFT and also with the help of convolution theorems. Computational complexity in past is n log n. This is a Vandermonde matrix. It is Vandermonde matrix of the endpoints is defined here. You see the first column contains all the powers up from 0 to n minus 1 powers of the C naught, and final last column contains the powers of Cn minus 1. And this is again multi-point polynomial elevation problem. You see, as I mentioned at the very beginnings, this is a problem actually we have to solve. The again computational complexity is O n to the power 2. We have realized that there is a close relationship between this problem and the Vandermonde matrix vector multiplication. This problem again can be reduced to the or convert to the matrix vector product of this. You can see entire problem can be given using this matrix equation. F is here column vector is coefficients of F, and here square matrix is a matrix transform of the Vandermonde matrix. If you can efficiently compute this matrix vector products, that says that we can efficiently compute the MEP problem, that is a multi-point elevation for polynomials. Here, to apply the concept of circular matrix vector multiplication, FFT, and the Toepi's matrix vector multiplication, we factorize the VT, the transform matrices or matrix of the van der Monde matrix, into the n factors of square matrices, so that each square matrix contains Toepi's block along its main diagonal and 0 blocks in off diagonal. You can see this is a matrix factorization of transform matrix VT. Here R Li is defined as a comprise of I is a unit matrix or identity matrix of order 2 to the power k minus L, and M, Li and Gli. The MLI is an upper triangular Toepi's matrix, and GLI is a lower non-singular lower triangular Toepi's matrix. This is the products you can see. This product again, V naught T and Y. If the V naught T contains the Toepi's matrices, therefore this vector matrix vector product can be used in the computed using the Toepi's vector multiplication. And also we can similarly get the vector matrix product for the van der Monde matrix matrix vector multiplication. And we have proved actually this also can be done in the computational complexity of n log to the power n. That means we can evaluate the multi-point polynomial evaluation problem with the n log to the power n arithmetic operations. Here, Chebyshev polynomial and Chebyshev norms. Actually, we have implemented these algorithms in matrix laboratory software, which is abbreviated the MATLAB, in order to evaluate the Chebyshev polynomials at the Chebyshev nodes. You can see here Chebyshev polynomial of first kind is defined by this recurrence relation, three-term recurrence relation, and the Chebyshev nodes is defined here cos j phi over n for j from 0 to n. And we have the numerical test, numerical experiments. We both again the direct and pass algorithm were implemented in MATLABs, and we measure the CPU times for each algorithms to examine the efficiency of them. These are the numerical outcomes, numerical results we got. First column indicates the size of the problem, and the second column indicates the time taken for direct methods, and the last column indicates the time taken for fast method. We don't see the much difference the time difference between these two algorithms, let's say n less than 16. But this time distinction becomes well dominated for large value of them. Therefore, this is fairly good algorithms for the large size of the problem. This is graphically I have shown things. This dashed line indicates the time taken for direct method, and here solid line, it is just slightly above the t-axis or x-axis, indicates the time taken for the fast method. Even it is difficult to see in the same graph, so we have drawn in the separately in here. This indicates the time taken for the fast methods. Okay, then the conclusion. Even though this is a quite fast algorithm, it provides the unreliable results or answers for large values due to its numerical instability. Therefore, this algorithm requires some numerical treatments for its numerical stability. And most probably, we hope to discuss the numerical treatments for its numerical stability in a forthcoming paper. And with that, I'm going to turn out my presentation. Thank you very much to all.
Thank you, Mr. Gunratna. His paper is also the joint author, Mr. H.M. Nazir of the University of Peradeniya, Department of Mathematics, is a co-author. Mr. Gunratna is a graduate from, is a mathematics special graduate from University of Peradeniya. He is currently following an MPhil degree again at the PGS Peradeniya. Thank you very much, Mr. Gunratna.